Hello, my name is Denis Sergeev, and today I'm going to present you some of my recent simulations of convection over a range of atmospheric conditions on TRAPPIST-1E. I would like to thank my collaborators listed here and also the organizers of the workshop for allowing me to present my work here. Feel free to pause here and read the talk outline, but I'm going to jump right in by saying that convection is one of the most important drivers of the atmospheric circulation and heat redistribution on tidally locked terrestrial exoplanets. But of course, it's more complex than this simple schematic shows. It involves a lot of different processes interacting on small scales. And so there is a wide scale separation between convection and planetary scale circulation, which means that for most GCMs, convection has to be is a subgrid scale process and has to be parameterized. So the question is, what parameters to choose? What parameterizations are the best? This question can be addressed by a range of different models. In my work, I use the UK Met Office Unified Model, which has a full suite of physical parameterization of convection, including the standard mass flux scheme, which tries to represent the convective processes as close to reality as possible. But the drawback is that it has a lot of tuning parameters optimized for the Earth climate and weather. We also have a simple convective adjustment scheme, which has only two free parameters, and so can be applied to more extreme climates of exoplanets. And this scheme interacts with both with the clouds, large-scale cloud, and boundary layer parameterizations. So the first question that I'm going to ask is, what GCM parameters is TRAPPIST-1E climate most sensitive to? For this, I use the TIE protocol have1 setup, and I start by running the control simulation with the mass flux scheme. I then run 3 more simulations where I swap the convection scheme to a more simpler one. I then go back to the mass flux scheme, but change only one parameter within it at a time. I also run 2 more simulations where I change the cloud scheme, and 4 more simulations with different boundary layer parameters. So let's look at these simulations from the perspective of troposphere temperature and wind vectors, starting with the control and then all the sensitivity simulations. So a brief glance is enough to see that a few simulations stand out, and some of them are actually associated with the production of different thresholds of convective cloud formation, as well as clouds and boundary layer. They also see differences in the cloud area fraction, and this results in different water content at the terminators, which can be summarized by this bar plot, where I'm showing the difference relative to the control in terms of the total water vapor averaged over east and west terminator. And on the right, I have the same plot, but for the total cloud water content. So in a nutshell, the TRAPPIST-1E have1 climate seems to be most sensitive to the parameters controlling the convective cloud formation rate and the interaction between the boundary layer and the convection. Some of them are enough to tip the circulation regime from fast to slow rotators. And this results in water content changes at the terminators, which may have an impact on the transmission spectrum. And a winner in this competition, so to speak, is the adjust simulation. This is where we choose to simulate convection with the simple convective adjustment scheme. So let's apply it to other climates. So the next question that I'm going to ask is, for what atmospheres, and specifically for what atmospheric composition, does the changing the convection scheme have the biggest impact? For now, I've been using the have1 configuration, which is a nitrogen-dominated atmosphere with 400 ppm. And you also know that in the TIE protocol there's hub2, the CO2-dominated atmosphere. In addition to them, I run 5 more simulations listed here: pure nitrogen, have1 with methane, modern Earth, RTNK-C, and hub2 with methane. So for each of them, I run the simulation with standard configuration and the mass flux scheme, and then swap the mass flux scheme for the adjustment scheme. We can see here the results of these simulations, and first of all, of course, there are differences between each of the atmospheric compositions because of the different greenhouse effect. But you also start to pick differences between the top row, mass flux, and the bottom row, the adjust. You can see this more clearly if we average the surface temperature for each longitude, which gives us the originally averaged profile. And this figure at the bottom shows the that using the adjustment scheme results in overall increase in surface temperature for all 7 atmospheres. The increase in temperature also is seen in the mid-troposphere, which is shown here, along with the wind vectors at the same level. And if we concentrate on the day side and average the zonal wind there, we see the salient features of the circulation on the day side, and they are correct for all the compositions. Here, they are characterized by superrotating zonal jets, which are located at the extratropics in each hemisphere for each planet. And the strength of this zonal jet depends on the convection parameters. So the adjustment simulation results in warmer climate in all cases, and it also overall enhances zonal jets in all cases too. And the biggest impact is seen for HAB2 simulation, but especially for the modern Earth shown in the middle here. So why does this happen? We can start to disentangle this by looking at the convective heating rates, which is shown here in colors for each of the simulations. To simplify the plot, we can average them again, but now this plot now represents the zonal profile of this latent heating. And this figure shows us that the adjustment convection scheme simulation results in stronger latent heating in the first 5 in the HAB1-like atmospheres and weaker convective heating in the HAB2-like simulations. The biggest impact is actually seen for the HAB2, but what is more interesting is what's happening to the modern Earth simulation. You can see that the shape of latent heating profile changes, making the heating to increase at the equator and decrease in the subtropics and tropics, which results in different temperature gradient from the equator to the pole. And via the thermal wind relationship, this likely results in the zonal jet acceleration, which indeed we can see if we compare the mass flux to the adjustment simulation. Okay, but what about the water content at the terminators in these simulations? This plot shows different profiles for mass flux and adjust simulations for the 7 different compositions. Then this is the same, but for the liquid cloud, and finally the ice cloud. So overall, the adjust simulation results in more water vapor at the terminators. But when it comes to the cloud water, both liquid and ice, it increases in HAB1-like and decreases in HAB2-like. But this has to be taken with a pinch of salt because these changes are, at least for some simulations, are likely to be within the time variability and uncertainty. Moving on to the second part of this question, how does the atmospheric pressure affect the changes in the convection scheme? So for now, I've been using the HAB1 with 1 bar surface pressure, but now I can change the surface pressure to different values ranging from 0.24 bar to 10 bar. And again, I ran the simulations first with the mass flux scheme and then with the adjustment scheme. The results in terms of the meridionally average surface temperature is shown here. You can again see the overall increase in temperature for all simulations. And there's also the enhancement in zonal jets for all 4 sensitivity simulations, as well as the control. So in a nutshell, the adjust simulation results in warmer surface temperature in all cases, except for the night side on the in the 0.25 bar simulation. It again enhances zonal jets. And the biggest impact is seen for lower pressure cases, which are shown here. And this is especially true for the 0.25 bar simulation, where the change in the convection scheme results in the flip of the circulation regime on the day side from the equatorial superrotation to symmetrical zonal jets. And I'm not showing it here, but at the terminators, we see the increase in water vapor analogous to what I've shown before. But the vertical distribution of low-level clouds is different, and this is especially seen for the liquid phase. So to sum up this part of my talk, and to my preliminary conclusions are that the TRAPPIST-1E is indeed, its circulation is indeed on the edge of slow and fast rotating regimes. It is sensitive both to the atmospheric composition and pressure, and different atmospheres respond differently to convection, clouds, and boundary layer parameterizations. Most sensitive cases simulated here appear to be the modern Earth, HAB2, and also the low pressure 0.25 bar with HAB1 atmospheric composition. The most important group of parameters affecting the climate seems to be the one that affects the convective cloud formation. And the regime change that we see in some of the simulations is likely due to different profile of convective heating on the day side. And all cases show water content change at the terminators, which prompts me to, in the near future, to make synthetic transmission spectra and see if these changes are large enough. And finally, I want to also investigate the circulation change mechanism with more detail. But what I'm doing now is I'm running the high resolution simulations for different compositions and pressures that I've shown before. So in the next minute, I'm going to briefly show you what I've done so far, namely how HAB1 and HAB2 look in the high resolution simulations for the substellar region. The high resolution setup is analogous to what is described in my paper published in the Astrophysical Journal this year. But essentially, it involves running a global model, which is a parent model and supplies initial and boundary conditions for the regional model, which is run with a convective permitting high resolution simulation, high resolution grid of 1.5 kilometers, where convection is simulated explicitly. And the motivation for this is to benchmark the global simulation in the absence of in situ observations on exoplanets and to explore small-scale circulation in detail. And this snapshot, for example, shows updrafts and downdrafts for these two atmospheric compositions, and you can see that there are differences not only in the strength of the updrafts and downdrafts, but also their pattern. And this presumably results in a different distribution of thermodynamic variables. For example, we see indeed that the cloud fraction profile for this region is different. In high res, there are more clouds. But there are also biases in the global model when it comes to different cloud phases. Overall, the global model tends to underestimate the low-level liquid cloud and overestimate the upper-level ice cloud. And this agrees with our previous cases of TRAPPIST-1E and Proxima b, which is described in my paper. And but the question remains, how would this affect the global climate? And with that, I'll leave you. Thank you.